So I hope my screen would be visible as well.
Yes.
Yeah, great. Thanks. So, yeah. Let us start with some problems. Okay. So, uh, I am posing a problem here. One core with certain windings. Yeah. So here in this magnetic circuit, a stack length of this core, basically these are iron core or any high permeable core whose permeability is infinite, and its stack length is 2 centimeter. Its inner diameter and outer diameter. So since here it is given in terms of radius, so Ri, let me provide. So it is 3 centimeter and Ro is 4 centimeter. Okay. And air gap length G, it is 0.5 centimeter. We need to compute the inductance of the core. Okay. So how to proceed with that? In last session, we have solved certain problems, one or two, I guess. I think one I told you to solve after the session, so I hope you might have done that. So this problem is also based on that concepts. So we need to uh, add two reluctances which are in series, or even though if you can compute the reluctance of air gap and then you find inductance, that would be more or less equivalent to reluctance of the overall circuit. Okay, so uh, any approach do you have in mind how to compute inductance? Could you suggest?
N square by R.
N square by R. Okay, you mean N square by reluctance.
Ah, yes.
Okay, so fine. Inductance, I will write what you just told. N square by R. And how to compute R?
L by mu.
L by mu. Okay. So L should be, if we are computing the reluctance of air gap only, L should be Z and mu A, and A will be how much? How to compute area in this case? Area of air gap. Assume it is in three dimensional, and practically it will be in three dimensional. Okay, so the length is air gap that is given, right? This L is given. So other two parameters which are perpendicular to this length. So one is a stack length which is in z direction, right? So that length is given as 2 centimeter.
Oh, that is stacked in.
Yeah, stack length. 2
Okay.
centimeter is the stack length.
And
Whose
this is 1 centimeter.
and 1 centimeter would be, yeah, difference between the radius of the core. So this length is 1 centimeter. So if we multiply 2 centimeter into 1 centimeter, that will give us the area 2 centimeter square. Okay. Air gap length you already know, that is 0.5 centimeter. So we will plug in all those values in RZ. So 0.5 centimeter. So we will convert into a standard format of SI units. So it will be meter into mu naught will be 4 pi into 10 to the power minus 7 into area 2 centimeter square. So if we convert into meter square, we will multiply with 10 to the power minus 4. Okay. So how much it will come? Zero point 0.5 divided by 4 into pi into 2 into 10 to the power 9.
So 19.89 into 10 to the power 6.
Yeah, correct. 19.89 into 10 to the power 6. Okay. And its
Yeah.
unit will be ampere
MM by
turns. Yeah,
ampere turns by
ampere turns per
Weber.
Weber. Yeah. So we computed reluctance and we know inductance is n square by r. So number of turns are given. Did I mention it? Number of turns are 75. Okay. So L will be 75 square divided by 19.89 into 10 to the power 6 will be, is it 0.28 millihenry?
2.82 micro.
Okay,
Oh,
I hope you
sorry,
must
sorry.
have got
It
2.
is 75. No, sorry, I think you are correct.
Okay. So 0.28 millihenry is the answer for this problem. Okay, any doubt about this problem?
Yeah.
Yeah, so in such case where high permeability material is given and air gap is also mentioned, then you could conveniently ignore the core material reluctance, right? So that would not impact much to the answer. It will be significantly less compared to whatever the reluctance of air gap you will achieve. So that's why here we ignore the reluctance of the core. Ideally, it should have been the addition of reluctance of core plus air gap. But here,
Huh?
in such cases, we can ignore it. Okay. So let us move on to another problem. Okay. So the problem is on the screen. Here we need to compute the permeance of the core. Okay. So in this problem, it is mentioned that inductor is made by winding 10 turns on a ferrite core, whose air gap length is also given, and it is supplied by a DC source of 100 volt, okay, and it is being switched for half of the switching period, and during that switching period, when the switch is on, the peak value of the inductor is 5 ampere and the initial value of current in the inductor is 0 ampere. Then we need to compute the permeance of the core. Okay. And permeance unit is also given here. Okay. It is microhenry per turn square. We need to provide in those parameters. So, what should be the approach to solve this problem? Any hint, any idea? Could you provide?
Actually, we have to find L by n square,
Yeah,
uh,
L by N
which is
square, that's all. Yeah. So
okay. So we need to
to find out inductance, how should we proceed with the given parameters in the problem? how to find out inductance in this case.
Yeah, the current slope is given.
Yeah, correct. Current slope is given, voltage is given, and when voltage is given, then you can always apply V is equal to L di by dt. So let me write that equation. 100 volt is being provided for 50 microsecond. Okay, so 100 volt we can write inductance we want to compute, and the change in current is observed from 5 ampere to 0 ampere. So it will be 5 divided by the time for the on period is 50 microsecond. So if we solve it, we will get 1 millihenry. So we computed the value of inductance. Now to compute
Voltage is
per
100 volts, no, sir.
voltage is 100 volt. Okay, okay, yeah, yeah, correct. Sorry. So 100 volt is there. Yeah, but still the inductance value is same, 1
Mhm.
millihenry. Permeance is inductance by N square, and that is 1 millihenry. We need to convert it into microhenry. So we can write 1000 microhenry. I think some noise is coming from background. Could you please mute yourself? Hello, Raja Sekar, I think. Yeah, okay, thanks. I think the noise is coming from your side. So if you are not speaking, please mute yourself. Okay, so permeance here is 1000 by number of turns is 100, sorry 10, so a square of 10 is 100, so it will be 10 microhenry per turn square. Okay, any doubt in this problem? Okay, if not, then let me pose another problem. And please read the question carefully and provide some approach how to proceed with this kind of problem. So CT here stands for current transformer and PT stands for potential transformer. Okay. So in CT also you can say N1 I1 is equal to N2 I2, and in PT V1 by N1 is equal to V2 by N2. Okay. So in this problem, CT is given with primary turn of 1 and secondary turns of 100, and cross sectional area of its turns, or if you combine all the number of conductors, so it will have a cross section area of 25 mm square where all the turns are placed. and this CT is now connected as a PT in the forward converter. As we have already studied, in forward converter we use transformer, and in terms of potential transformer only, and with one turn primary, same in same manner, and 100 turn secondary. The maximum flux density is given up to zero point 0.2 Tesla it can tolerate. Okay. Core demagnetizing is achieved using a Schottky diode and resistor configuration, which were a lossy configuration, right? If the forward converter is switched at 100 kilohertz and 50% duty cycle, then we need to find out the output voltage of the forward converter. Okay. Yeah. So what should I do? From where should I start?
We have that turns ratio into duty cycle, output voltage.
Yeah, first we will write the relationship between output to input. So that will be V2 by V1 is equal to N2 by N1 into D. Okay. So if somehow I can find out the value of V1, all other parameters are given, right? N2 is given 100, N1 is given 1, D is given zero point 0.5. If somehow I am able to compute V1, then V2 I can easily compute. So V2 is nothing but 50 V1. Now the next task is to compute V1. So tell me how to proceed with calculation of V1.
So magnetizing inductance, for finding the magnetizing inductance, the data is given.
To find out the magnetizing inductance, you are saying data is given. Okay, so first of all, why do we need magnetizing inductance here?
Because that is V1 by Lm is the primary current.
Okay, so you are telling that if somehow we can relate the voltage with flux.
Yes, sir.
Okay, so yeah, so if flux maximum flux density is given, okay, let me recall the graph of magnetizing inductance. So the flux was rising and falling in a time period like in such a manner. It is phi max dt and t. This is flux. Since we are given with flux density, maximum flux density, so phi max we can compute with B max into area, cross-sectional area of the core, right? So, which is 25 mm square is provided in the problem. So, I will compute it. 0.2 into 25 into 10 raised to power minus 6. So, it is 5 microweber, right?
Yes, sir.
So, it is fine till this point. Now, since we have found the phi max and it is varying from 0 point, as we know from forward converter it should start from 0 and it should reset at 0. So we have, first of all, let me write the relation of voltage with flux. So n d phi by dt, and since we are dealing in primary side, so we will write all the primary voltage and number of turns on the primary side. So it will give us N1 is 1 given in the problem. The change in flux is 5 microweber and it is changing in time period of 50% of duty cycle. So let me write zero point 0.5 into t, which is nothing but the inverse of f. So f will go in numerator and it is 100 kilohertz, which means 10 raised to power 5. So if I will compute it, I will get 1 volt. Am I right? I hope I am right.
Yes, sir. Yes, yes.
Okay. Then we already have found out the relationship between V2 and V1. So I can write V2 by V1. Sorry, V2 by 50 V1. And V1 is 1 volt. So V2 will be 50 volt. So from this example also you can see that if even this forward converter works as a buck converter, but here the voltage on the secondary side is significantly higher, almost 50 times of primary side. So that's another observation based on this problem. So I hope it is clear. If any doubt in this problem, please let me know.
Sir, its output voltage is 50.
50, yeah,
Okay. Okay.
because
तुम
we
कहाँ चलाए हो?
in the question itself it was mentioned to compute the output voltage of the forward converter.
This is secondary voltage now, sir. 50 is secondary voltage.
Yeah, it is secondary voltage only.
Then we have to multiply with the duty ratio to get an output voltage.
Yeah, this V2 by V1, this is output voltage V2.
So this V2 is output voltage.
Yeah, and V1 is input voltage. And we do not have tertiary winding here because of the lossy configuration. It is mentioned that core demagnetizing is achieved using a Schottky diode and resistor configuration. Okay, is it fine, Santi?
Wait,
Hello?
sir.
Yeah, go ahead, please. Hello?
Hello,
Santi?
sir. Sir,
Yeah,
wait, sir. I'm thinking about this.
okay,
Whether
okay,
this is V2 is across a load or across and secondary of an transformer.
okay. This
Sir,
relationship,
no,
if
no. It
you,
is just written.
yeah, go
Sir,
ahead.
it is just written as V naught, right? Instead of V2, we have to write V naught.
Yeah, V2 is V not here. V2 we have
Yeah,
considered.
and
Okay,
Vn
so
is Vn, right? That's all.
okay. I think you are confused with this V1 by
Ah,
N1 is equal
yes,
to
yes.
V2 by N2.
Yes, sir.
Yeah. This is just the notations here. Let me remove it for you. Let me call it E1 and E2. Okay. So now I hope it should be fine for you. So let me pose a last problem based on magnetic circuit. So here we need to identify the value of inductor, okay, and ripple tolerance is also mentioned, okay. So this is a conventional buck converter, and we need to compute the value of inductance if ripple is allowed as 10% of the rated current, and all the switching frequency and all are given. So how to proceed with this?
No, this del IL we have to find.
Yeah, so del IL is given, which is 10% of rated output current, which is nothing but the inductor current, average inductor current. So it is 0.1 into IL. Okay. And IL is nothing but I naught. And I naught is not given directly. However, load power we do know, right? So P naught is 12 watt, which will be V naught into I naught, and I naught we can find out 12 by V naught. V naught is 12 volt also, so I naught is 1 ampere. So it will be 0.1 ampere. Del IL ripple we have found out is equal to zero point 0.1 ampere. Now let me apply that volt second balance or voltage equation of inductor VL is equal to L del IL by dt. Okay. And during on period of switch, VL is equal to 20 minus 12 from KVL. So it will be 8 volt, and inductor we need to compute into del IL is zero point 0.1 ampere divided by duty ratio. I think we should be given, okay, it is not mentioned directly, so we can compute duty
Sir,
ratio
it is
directly.
12 minus 12.
Oh no, sorry, thanks. It is 20 minus 12. Yeah. So D is not given directly, we can find out V naught by V in. So 12 by 20. It is zero point 0.6. So zero point 0.6. T is nothing but the inverse of frequency, and frequency is given, so 50 kilohertz. We will write. Now L is 8 into zero point 0.6 divided by 50 into 10 to the power 2. Okay, 1 10 is cancelled by zero point 0.1, so it is 4.8 by 50 into 10 to
0.96 millihenry.
0.96 millihenry. Okay, so it is 0.96 millihenry. So we should have the value of inductance to avoid the ripple of 10%. It should not exceed the ripple of 10%. If this is the condition to design the inductor, then we have to design it with at least 0.96 millihenry. So I think you should go with a point or 1 millihenry. If such numbers are coming in computation, then you can go ahead with 1 millihenry of inductor value. Okay. So this
Sir,
was, yeah, go ahead, please.
uh, sir, if I say inductance, what are the standard inductances available in this range, sir? Can you say some?
Are you asking from product side, which brands or which, what
No,
do you
no,
exactly refer to?
no, sir. Anyway, we have 0.96 is millihenry is the answer we got.
Huh.
But yeah, anyway, we can if we do our same inductance on our own, then we can get this exact value.
Yes, yes.
But if we purchase the inductance, uh,
Then we can
what
purchase,
is the
we have to go for 1 millihenry. It would be more suitable, right?
okay. No, sir.
And
Is
what,
there any pattern in which the standard inductance are available? Suppose 1 millihenry and then 10 times of that, and then
yes, yes, all 5 times of that, such kind of products will be
no.
available. And nowadays, even you can order any custom inductance, like you want certain 4.2 millihenry or so. So you can order it and they will deliver it to you. But you want to just go to the market and bring back, then I think most standard will be integral values, 1, 10, 100 kind of thing.
Okay.
Sir,
Sir, is there,
Yeah,
sir,
please. Yeah.
this 4.2 millihenry you have just said
Hmm.
that we can have a custom made inductor.
Hmm.
Sir, where I in that Moser website, where we can get that custom made?
Anywhere,
Is there?
even IndiaMart or Mouser.com or there are so many electronics websites, right? Let
Okay.
me,
There,
yeah,
okay.
what are you
There
saying?
they will be having some standard values, but
Huh.
okay. But custom made can also be done.
Yes, yes, even Amazon also sells. Let me show it to you. If you can see the screen, so if you just Google search the by inductor, then you will see so many websites, right? Amazon, Flipkart,
Mm.
Mauser, and so. Element 14 is another website, IndiaMart, Future Electronics. There are so many websites. And if you open anyone, let me open Element 14, then it's go for fixed value inductor. Then you can see the data sheets and you
Yeah, but
can,
sir, here only we search for that custom made. For my mini project, we have searched some components here,
huh.
but we couldn't find that custom made.
Okay, so for custom made, you have to contact them. Okay, so you just write a mail to them that I need so or so value of inductor. If they
Okay,
are not available on the website, then some mail ID would be there to contact them. That you can do.
okay. Mhm.
Sir,
Yeah, please.
my question is that we can easily make these inductors, no?
Yeah, yeah,
Because
that
one
is,
similarly, but the toride, that is dust core, is to be required for these inductors to be made, because
yeah,
the or any specific material other than ferrite.
yeah, there
If I
are,
want to wind this 1 millihenry inductance and that much current, I
mhm.
think small ferrites can do that, are easily available.
Yeah, because ferrites are easily available material and cheaper also, and it can do our job very easily. So ferrites are preferred material, but there are so many cores. You
Course,
as
torides are better choose for their profile, isn't it, for inductors?
yeah, yeah, as we
But
saw just now. Yeah, yeah. Go ahead.
material,
Material ferrite,
toride also,
toroid in particular in toroid material, I think ferrite
because
is
there is no as such air gap in the magnetic path, na?
ha ha ha.
In toride, there we have to choose the material like that. I think so. In torides,
On that I am not sure as of now, but it uses, yeah, because of its better inductor. Let me see. Generally, toroid employs, its property of high inductance in the given area.
uh,
So that's why it is more preferable and it is compact as well.
yes.
But what are your factors? What you were saying about?
But torides, if there is no air gap,
Mhm.
then the toride material has to give that. Okay, this is the gap ferrite, or how to design inductor in torides. My question, direct question is that,
Okay, how
because
to
we
do?
know design,
Okay,
huh?
okay, how to design inductor in toroid. So,
Torides.
okay, so toroid is generally, it is the same material. The difference will be in calculation of area, right? So I
Hmm.
think we will solve one or two problem based on toroidal core. Or I think in the starting of the session we solved one problem based on toroidal core with air gap. So let
With
me,
air gap.
yeah,
With the air gap, huh?
air gap is there if you want, a variable parameter of, sorry, variable values of inductance. Then air gap is very useful. See this kind of code.
Here the inductor is having that gap. Preferably, it is gap.
Yeah, yeah, it is gap.
We have to cut the ferrite toride in this fashion.
Yeah, because see, core material is almost similar, right?
Hmm.
So its permeability will be almost similar. But to vary the value of inductance, if you need a certain value of inductance, So you cannot do much on core. So then you have to play on air gap side
Mhm.
or number of turns or current. So you have two or three degree of freedom. So wherever you want to play, if you have flexibility on current size, like you have higher limit on current, then you can go with higher air gap as well.
Yes.
Yeah. So that you need to see during design how much limit is there with you, how much to how much extent you can go. And
S-
yeah,
Sir,
yeah.
this cut in the core
Hmm.
for the air gap.
Hmm.
What are the ways we can do this? We can create this air gap.
Okay, how to cut this course? So there are many ways of cutting. Nowadays there are so many machines to cut the laminations. Okay, so if you can,
Suppose in our lab, if we want to do,
then you have
uh,
to go to mechanical lab. If in your college you want to cut this kind of course, then you go to the mechanical lab and there will be some instruments. I forgot the name. So which with the help of actually for lab purpose, we generally do the design of C core. So C core you will not get directly from the market. You will get a lamination of a square or rectangle and then you cut it in between. So see, in similar fashion here also, then you purchase a lamination of this kind of circular and you need to cut it with some mechanical instrument, I think related to saw or something. Uh, that I will search the name and I will let you know in the next session. Otherwise, nowadays machine cutting is very popular thing, but for such a low cost thing, you will not have the access of machine cutting. Generally, it is used in laminations of motors and transformers, high frequency or high performance things.
sir, the geometry of the core,
Hmm.
uh, yeah, it is having a definite influence on the value of inductance.
Hmm.
Uh, but is the if you change the geometry of the core, uh, there is nothing more complex in calculating this inductance, right? Because it is just the area and the length which is going to change.
Yes,
Uh,
yes. And also the direction of flux should be, low reluctance path. You should always try to provide the high permeable part to the flux. So if you curl your finger in the direction of current with the number of turns, then your flux should not see the barriers or it should not see the least reluctance towards the air. So you might have heard the terms of fringing flux and leakage fluxes and all. So if those will be high, then you are not utilizing properly your current and materials. And in this kind of toroidal core, compared to rectangular core, there will be difference in window area, how much window area you can have. So if we will try to take some problems on Windows area of toroidal core along with certain C core, and then we will see that where you are getting more area. Because ultimately, how much number of turns you can provide, that is limited to this area, right?
mm,
So,
no, this is the window area. Yeah.
so how much window you can utilize and where you can utilize more. So that is another factor that will help in lighter weight design. So generally toroidal kind of winding helps in those lighter design or lightweight design because it has relatively more window area if you can see.
So, sir, you are very correct because this is very popular design buck type of converters.
Yes, yes,
So
yes.
no, 99% I will find the buck converters with the toroidal
Perfectly.
interest.
Yeah. Yes.
Yeah, isn't it?
Yes.
Yes, it.
That's a good observation. Yeah.
Yes, and easily wound on the by hand itself.
Yes, yes, yeah, that's another factor. You can easily wound it with hand as well. However, up to certain extent, it is true for even conventional inductor also, and that rectangular inductor. But here it is more convenient. So, in if you want to introduce certain another shape apart from the existing shapes of toroidal core or rectangular core, so those cores will be more efficient or more optimal wherever you can incorporate high number of turns with the given area. Then that core would be considered as an optimal choice. And with that, even with that new type of core, if you are able to, channelize all the flux throughout the core material, so you are minimizing all the leakage and fringing and all, then that would be a good design. So if you will come across the design kind of thing, then you might take care of all those factors. Okay, then I think we should move ahead with the content of today's topic. So, yeah, my topic is about design only, the leftover portion of the design. So let me, yeah, so while designing the code, there are two most important factors that you must care. So could you tell me what are those two factors?
Material and
No, apart from material, I am talking about factor in terms of, certain parameter in terms of electric field, magnetic field, or conductors. Material is
for what man
uh,
for
uh,
design of core.
for design of material, absolutely it is important. But being from an electrical engineering background, you cannot do many things on material, right? So whatever material will be available to you, you will have to deal with that.
One is the window area factor.
You are saying window area factor, okay?
That is
That
KW.
okay, you are talking about factor only, not window area. Okay, KW, yeah. It is generally zero point 0.4 to zero point 0.6. So, while designing, how will you maximize window area factor?
Good craftsmanship.
Okay, okay. So I think you can innovate there, but from being from electrical engineering, I cannot go there. But yeah, there are certainly many ways to increase that factor, window area factor. But my point was, or my intention was that window area factor you cannot enhance from significantly from zero point 0.6, or maybe in excessive case you can go up to zero point 0.7, but there are certain other factors that you can play with. And so could you let us know what is woodcraft area, or what is that you told? So Mr. Dhananjay, right?
Ah, yes.
Yeah, so what did you suggested that how to improve that window area
Oh,
factor? Actually,
by
I am not aware of that, so I want to learn from you.
good craftsmanship. If the person who is going to wind the inductor,
Hmm.
he is skilled enough, then he can utilize the window area properly. If he is in taking consideration of creepage and everything,
Hmm.
then you can utilize that. Otherwise, if it is a poor craftsmanship, then he will be going towards point 3 or point 4 utilizing window area.
Okay, means how good is the design of that winding that will
Yes,
enhance the
yes,
window area factor? Okay. So those factors, let me write it. It is flux density and current density.
Oh, you mean parameters? Okay.
Yeah,
We,
parameters,
since
factors.
it is a factor, we are talking thinking like something unitless.
Okay, okay. No, no, sorry. I was talking about certain parameters.
Parameters. Okay.
Yeah. So why they are so important while designing the code?
Flux density will give the saturation of the core, because we cannot go more than that. For ferrites, it will be zero point 0.1 Tesla,
Okay.
and for current density also, that is up to 5
Hmm.
amp per centimeter square,
Sorry, mm square
or
it would be.
mm square. Sorry, 5
But
ampere per mm square.
but you are very correct about that value 5. So it is generally used for natural cooling, right? So up to 5 ampere per mm square, probably you will not need any medium of cooling. Otherwise, you will require additional cooling component or heat sink kind of thing. Yeah, so current density is limited, hence you cannot increase current density more than whatever 5 ampere per mm square you have. So, and it will increase losses also, right? Conduction losses or copper losses. If you increase current, then certainly it will lead to more losses. And if you operate core near to the saturation or beyond saturation, then we have seen the BH curve, right? Your B will increase very less compared to your H, and it will give. Sorry, I couldn't hear you. I think you might have some issue with your connection. Could you please repeat yourself? Okay, so we will hear from you after certain time. I think my internet connection is weak. Are you guys able to hear yourselves? Could anyone else speak apart from Raja and Mr. Dhananjay? Okay, yeah, I can't hear you guys. Okay. So my connection might be weaker. Okay, so if you are able to hear me, then let me complete this point and then we will take your view. So saturation will lead to, significantly core loss as you move towards higher flux density because hysteresis loss is generally kh into Bm raised to power x, and eddy current losses are Ke into Bm square. So it is dependent on maximum flux density parameter. Okay, so I think I can hear you. So could any one of you speak now?
Yes, sir.
Yeah, yeah, Mr. Dhananjay, I can hear you. So you were saying something.
No, no.
No.
Sir, can you hear me?
Yeah, I can hear all of you now.
Sir, this current density, we have set 5 amps per mm square.
Uh-huh.
Sir, this is a material property, right?
Uh,
Uh,
this,
if we are using a copper,
huh,
then the current density has to be within 3 to 6 amps per mm square.
okay.
If we are using some other material, then
Yeah,
current density changes.
it is generally 3 to 6 or 4 to 6 or whatever. But generally, as a rule of thumb, we take 5 ampere per mm square. You can exceed to 5.5 or 6, up to 6, you can go and you might observe certain things. But 5 ampere per mm square is considered as very safe values. So if you are designing and you do not want to redesign, if you want to finalize a product with certain current density without any cooling medium, then you take safe value of 5 ampere per mm square. But if you will stretch this value, even with any material, copper, aluminium, whatever, if you will stretch this value up to 6, or even if you will stretch it further, then you might see that losses are more and there will be certain requirement of heat sink. Okay?
Sir,
Yeah.
one more advantage of winding this buck type of converters with ferrite or whatever the material for the uh, inductor,
Yes.
that we can wind the solid wire with the said AWG or SWG,
Okay.
because we need not have to consider leads wire here,
Huh.
because this ripple current is going to take place and that is surfacial.
Okay.
Yeah,
Okay.
so we can wind directly with the bare copper wire, bare copper, yeah, insulated copper wire,
Hmm.
that is easily available. We need not have to go for
Leads wire.
leads wire. Am I correct?
Okay.
For
So,
inductor, at least for
e
inductor, not for transformer.
huh. So, see, let me talk about this list why these are required and why solid wires and where solid wires are preferred. So, see, generally, if you will use solid wire, then and indirectly we are operating in alternating way of current, right? So
Yes.
we have certain switching frequency, we have core material. So there are two types of losses which are known as a skin effect loss and proximity effect loss. So those are dependent on a skin depth of the conductor. So let us say that a skin depth of the conductor is equal to under root 2 by omega sigma mu. Okay. So mu of material anyway you cannot change. Sigma is the conductivity of the conductor and omega is the frequency of the circuit, whatever you are using. So let's suppose you are using a solid wire. Okay. It is a solid wire. Generally we use a stranded wire, but let us suppose you have a solid wire and its radius is uh, 1 mm. Okay, R is 1 mm, and a skin depth, since we are using 100 kilohertz of frequency or so, your skin depth might come about zero point 0.5 mm. So effectively you are utilizing only this much area. Zero point 0.5 means half of the conductor you are utilizing at that frequency. Then in that scenario, either you will need to reduce the frequency of the circuit, that will again lead to another problems, because if you will operate at lower frequency, then of course your responses and other factors will be affected. But the another thing is you are not utilizing your given area, window area properly, because you could have managed with the half of the area of that conductor. Even if you place half of the area of the given conductor at that frequency, that would generate the same amount of power or same amount of output performance. Those are required. So here, if you are using 5 ampere per mm square with this kind of AC a structure or this kind of a skin depth, then effectively you are using 2.5 ampere per mm square. You are utilizing a space as 5 ampere per mm square, but effectively you are having 2.5 ampere per mm square, and that is not optimal, right? So to avoid those uh, a skin depth, and due to a skin depth, that AC copper losses, they are known as, let me, because they generate because of our AC supply or AC operation. So skin effect and proximity effect. So that's why we generally do not use a solid conductor. Instead, we use a stranded conductor. So if you have this kind of width of obviously 1 mm, so in 1 mm of place, we use this kind of stranded wires to make one turn. Here, solid conductor, one conductor will make one turn, but here you will need certain number of strands to make one turn. But what are we losing here when we are going for a stranded wire? Can you observe this kind of uh, arrangement, and could you think of what at what terms we are losing?
Stranded and insulated.
Of course, they all will be insulated because without insulation it won't be feasible. So, do you know fill
the
factor?
the the, the,
Fill factor.
the effective cross section reduces.
Yeah, that's mean fill factor. So, the area of wire divided by area wherever that is placed. So, these effective places, they are vacant and you cannot utilize these kind of places, right? Once they are filled in this manner, then they are unutilized. So your fill factor is again reduced. So in solid conductor, you place a conductor and that will occupy the entire space. But with a stranded conductor, you will need certain space between them. And even if you do not need them, they will be there because once you will go for hand winding, you will see, or even with machine winding. Generally, we consider in machine slots, motor or generator slots, fill factor of zero point 0.4 to 0.45, which is indirectly meaning that you have lost more than half of the area, slot area or window area that you could have utilized. So that advantage comes with solid wire, but again the with solid wire you will have significantly a skin effect and proximity effect at such a higher frequency. So to overcome this stranded wire, again people came up with this wire, which Mr. Dhananjay mentioned just this wire. So it has very a small strands, very small, very small. So what they will do, they will further improve the, you know, even with this kind of a standard wire, if you have such a high frequency, there might be possibility to have certain AC losses. So to further reduce or almost eliminate the AC losses, we try to make a stranded conductor or a stranded turns so thin such that its a skin depth will always be higher than that depth. So you can overcome the AC losses. Any doubt in this?
So this reduction in fill factor
Hmm.
is we are getting is mainly because of the insulation
Because of
and
insulation, and you cannot place because these are round wires, right? So you
mm,
cannot place, you will have certain spaces left. You cannot
okay.
fill entire space.
Sir,
Hmm.
actually we are going for this stranded wire.
Huh.
Uh, anyway, for in each strand, the skin effect will be there, but
Hmm.
but the current is but the over across the cross section, but the current is equally distributed more or less. Uh,
Yeah,
that is the reason. Is that the reason, sir? Okay.
that is the reason for what?
No, no. Uh, we are going for the standard wires because if you use solid conductors, we have skin effect. That's why we are
Yeah,
going here.
because here, the area of a strand is such a
Uh,
less so that your skin depth will be higher than that area, right? So if a skin depth is higher than your conductor or a strand diameter, if it is higher than radius of a strand, then you will not lose anything on AC losses. Did you get the point?
sir, if skin depth is uh,
See,
greater than the radius, okay.
a skin depth should be either equal to or less than the radius of the conductor.
Yeah, less than. Okay.
A skin depth means how much you can utilize the conductor area. If you have very high frequency, it means you are absolutely near the surface. You are not utilizing out of inside the surface. So if
Yeah,
you are
sir. My
using,
question is,
Mhm. Yeah.
sir. My question is, the anyway the
Hmm.
individual strands will experience skin effect.
Yeah,
But
yeah.
since all the strands are having skin effect, it might look like the current is equally distributed across the cross section.
No, no, no,
That's
no,
why
no.
we are
No,
okay.
no,
Okay.
no. It is not that a skin effect is distributed uniformly around all the conductors because first thing
Strands.
it will strands. First thing it will not be uniform even if it will be
Okay.
present, and second
Mhm.
thing it will depend. It will depend where it is placed and how much the skin depth of those conductors. So for this frequency. See, a skin depth is dependent on frequency, current conductivity of the material, whatever you are using. So once it is designed, it will not matter how much dimension of the conductor you are using. If you are using a smaller conductor diameter, sorry, a strand diameter, then it just implies that you have conductor with a skin depth higher than the radius of that strand. It means you do not need to worry about AC effect there, AC loss effect or a skin or proximity effect there. But wherever you have a strand radius higher than the
Okay.
skin depth, then you will need to worry. Yeah.
Sir, if skin depth is higher than the radius of the strand,
Mhm.
then at higher frequencies there might be a possibility that some strands we might left out, we might leave out. It's been
At higher frequency, your skin depth will also reduce, right? It is a function of frequency.
yes, sir. But if
Yeah.
skin depth is greater than the radius of strand,
Hmm.
then we might lose some strands. Even though it is stranded, we might lose some strand on the surface of the conductor.
Then it is possible. See, you are correct, but in other way, then it is possible that current density is not uniformly distributed. Right? You mean current density, because if in such a manner, it means, some strands might not have such whole area utilization in the mission of providing certain amount of currents. Then current density distribution might be non-uniform, but a skin depth is always same, no? Because a skin depth, it will not see any different apart from these three factors.
Sir, here in this equation of skin depth,
Hmm.
there is a permeability on the bottom, root of 2 by omega conductivity into mu.
Huh.
So this permeability is the permeability of the material wire we are using. Is it?
Yes, yes, yes. And these coppers are not highly permeable materials, so it will be similar to, near to the air kind of thing.
Mhm.
But mu will be always same until unless it is a highly permeable material. But you have two degrees of freedom. One is frequency and one is the conductivity. So whichever way you can change either the material to change the conductivity or to use, lower conductivity material. But for using lower conductivity material, it has another disadvantages, right? Because here, if you reduce the conductivity, you will gain in terms of a skin depth. Then you are having upper hand on a skin effect and proximity effect, but you are losing one in one way on the conductivity,
Mhm.
because if you have lower conductivity, your resistance will increase and you will lose in terms of DC copper losses, which is generally IRMS square R, ohmic loss. So ohmic loss is known as DC copper losses. Let me just write it. And AC copper losses, it is AC copper losses are generated by a skin effect and proximity effect. Okay.
Okay. Sir,
Do
this
you,
Litz
huh,
wiring,
sorry?
this Litz wire we have discussed.
Yeah,
Uh,
this lit's wire we use to eliminate the AC copper losses.
uh, Sir, is the cross section is the only difference? It is
Yes,
also
yes.
standard, right?
Yeah, it is also a
Okay.
stranded, but it is so thin that in
Okay.
at any given point you will have a skin depth higher than the lit's wire radius.
Okay. Okay. So the fill factor will be higher in this
You
Litz wire.
cannot say on fill factor because effectively you are using a stranded, right? Just that
Okay.
a
Yeah.
strand area is less, not your fill factor and wire area is cha getting changed.
Mhm. Because if as the strand size it reduces, uh, the air gap in the inside the strands can also reduce. That's my
Yeah, but number
insight.
of strands are increasing here, right?
Mm-hmm. Okay. Okay, sir. Okay,
Okay.
we can go ahead.
So anyone has any other doubt? Yeah,
Sir,
go. Yeah.
my point was that you in solid conductor,
Mm-hmm.
let the surface area, current
Mm-hmm.
flow through the depth of skin depth.
Mm-hmm.
If that depth is higher than your delta I utilization,
Uh-huh.
because delta I is going to use by this depth,
Yes.
depth of penetration. So
Mm-hmm.
that skin depth has to be larger than that delta I penetration.
Yes.
So it can be flow on the surface and
Mm-hmm.
let the DC current flow on the center core.
Okay.
So that time, in that way, my AWG, whatever the 12 or 14, whatever the higher AWG comes,
Mm-hmm.
we need not have to bother depth of, because it is DC inductor. This is
Okay.
only the DC inductor. But in transformer, this is not the case.
Hmm.
So there we have to have use this leads wire, but here we need not have to. I think so. If I
Okay.
am
Okay. So you are saying that inductors
inductors
for
specifically
inductors
DC
only.
inductor.
Yeah, yeah. For
Okay.
DC supply, you never
Very
need
easy
to.
to
Yeah. Yeah. You never need to worry about AC losses or a skin effect.
AC losses is not at all. I think so.
Yeah. Yeah. You are correct. Yeah.
Because that we have to understand that when they are flowing,
Hmm.
let they flow on the surface, but that depth should be higher than your flow of AC current,
Yeah. But
delta I.
yeah.
Because
That
the delta I, we have to think over that.
delta
And
you
our
mean ripple?
DC current of the inductor, that average current,
Okay.
will
Okay.
be mainly flown through the core of the cross section.
Okay. You meant this delta I, right?
Yes, yes.
Okay. This ripple.
Ripple, and that has to flow through below the depth of skin depth.
Okay. Below the skin depth means on the surface.
So on the surface, okay, then you are utilizing that conductor very well.
Oh, okay, okay. Okay, what,
This is beauty of winding the inductor. I think so.
what you meant that ripple is has some certain frequency. So
Yes.
it can flow on the surface because of lower skin depth,
Hmm.
and all the average current should flow with the our
Yes.
conductor. So okay,
Yes.
now I got it. Yeah.
That is interesting part of that
Yes, yes, yeah. That is the beauty of design. What approach
design.
you
Yes.
take
Yes.
here.
Yes. Yes. Yes.
Okay. Yeah. So if others have any doubt regarding this, you can clarify here.
Sir,
Yeah.
sir, is there any tools through which we can see this visually? Any
Wh-
online tools available?
Where you can work on design part, you were asking.
No, 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 sir. Just looking at this current flow cross section
Current flow cross section of, I mean, to
on,
visualize
yeah,
a
yeah, on
skin
the
depth and
conductors.
all. Okay.
Yeah, yeah. We are saying these theories, but is there any way?
Okay.
I just want to know.
I haven't searched because mostly we design in certain softwares, but let me write this point. If I will see if there are certain free websites to visualize, then in next session I will definitely let you know. AC losses and skin depth. Okay, so I have noted it. I will look it, and if there are certain websites, then definitely I can show it to you in the next session, or I will mention those website names. Or in parallel way, you can also search on your own. If you see, you can also let others know.
Yeah.
Okay,
Okay.
so yeah. Okay then. So we concluded that there are two most important parameters to design of magnetic, right? So one is flux density, other is current density. So flux density determines the core losses in the material or in the circuit or in the device, or and current density determines the core losses, right? Sorry, copper losses and conduction losses. So generally, as we are studying power electronics, we are concerned with two types of magnetics design. One is inductor and other is transformer. And those should be high frequency, okay, not large, bigger devices. So high frequency are small inductors and transformers. So they will have 2 or 3 degree of freedom. One is, of course, core area, window area, current density, flux density with materials, number of turns you can play with. There are so many things, but of course, you need to, optimize or see where you will go by which approach. So there is one terminology which is area product, okay, which is very popular area product. It it tells you how much, core window area and how much cross-sectional core cross-sectional area you will have, and it gives you certain analytical assumption beforehand you enter into design, right? So you should have certain analytical equations before you enter into practical design. So whether it should be effective or not. So area product is core window area or window area. It is nothing but a window you can denote it with. Other is cross-sectional area. So we will represent it with A core. Okay. Now, how to compute window area AW Could anyone help me in the expression of window area? How much will be window area? Okay, so it is generally written with a factor, window area factor into window area. Let me write it for convenience on the left side. Of course, we are not going to utilize complete window area, so it will have certain amount of factor which is denoted by KW, and AW is complete window area. It will be equal to number of turns into area of conductor, and generally it is denoted as summation Y in Y a conductor. So let us suppose you have a conductor whose area is certain A and you have Y number of turns. Then if you multiply them and add them, then you will get the product of a window area and window area factor, and generally window area factor varies from zero point 0.4 to zero point 0.6. So we write window area as 1 by kW because window area factor is known quantity. So a conductor Y. Okay. So this is core window area, and the if so there are two parameters in core window area. One window area factor we know. One is number of turns, that how many number of turns you can incorporate, and another is area of conductor. And area of conductor you know, that is RMS by J max. So J max you will have to decide initially when if you know the rating of the material, then you will need to decide the Jmax. If you are going for natural cooling, you can decide Jmax is equal to 5 ampere per mm square. Okay, so Jmax will be fixed beforehand, and area, if you want to know how much area of conductor you should choose, then you will again have to rely on the rating of current. So in those ways you can find out either one thing if you know one thing. So you should try to reduce unknowns while going for design. So here the purpose of providing this, that JMax will be generally known to you. Okay. So you will be left with current and area of conductor. That also we will further see how much the value of current and how much the area of conductor you should be using and you will be required. So that we will see.
Sir, this JMax,
Mhm.
uh, for natural cooling, you said that it can be limited up to 5 amps per mm square.
Mhm.
So if suppose we are using forced cooling for the conductors,
Huh.
then can it be increased beyond 5 also?
Yeah, definitely. For if you will use forced cooling, then how much cooling you are adding additionally,
Okay.
right? That will be
Mm.
dependent on the current density. If you want to use 10, then you will need certain amount of cooling. If you need 15, then you will need more cooling, right? But you can go ahead, yeah. You can increase that value. So that's why Jmax should be known, and Jmax should be known on the basis of how much cooling you are intended to provide. Okay. So let's say if you are saying that you want very high current density, means very compact, but you are saying you are not worrying about how much cooling it will take. Whatever it will take, I can provide, but I want to go with high current density. Then you can certainly go with very high current density. Is it okay?
Yeah, yeah, yes, sir, yes, sir.
Okay, okay, cool. So yeah, So let me put it in another equation, or let me just extend the upper equation. Kw J max, I'm just plugging the value of area of conductor in this equation, in equation 1. So here it will be Ny into IRMS. So window area is indirectly uh, equal to the ratio of MMF summation divided by your window factor and Jmax. So now see, initially we reduced the unknowns to two terminology, IRMS and area of conductor. Now here you can see that it has come to Ny into IRMS divided by Kw into Jmax. Now you know the Jmax, you know the window area factor, and on numerator n into I is the fact is the other parameters there. Now n I is nothing but mmf, you know, and mmf is directly related to flux density, and from the material data set you can select how much H or how much ampere turns you are willing to provide to have the allowable or maximum flux density. Okay, is it clear? Now you can decide how much Ni you can use for the given material. That's what I am trying to tell you.
from the value of Bm.
Barrier is Bm here. So limit will be Bm. So let's suppose you have certain material and you have this kind of curve. So where do you want to operate? You obviously you would not like to go in saturation region. So let us suppose you are operating at this point. So this has certain 0.2 Tesla and it has certain H magnitude.
Yeah.
So you see that H magnitude, and according to that H magnitude you come to and you equate it to N into I. Okay. Now
Mm.
you see how much number of turns you can accommodate. If you have sufficient number of turns you have selected, or you know now how much number of turns you can accommodate, now you are indirectly getting the current rating of the device, right? So
Mm.
in such a manner you can select the current rating and number of turns and all those
Current rating of
things.
conductor.
Sorry, what conductors?
This is current rating of conductor.
Current rating of conductors, yes.
So with the number of turns, we can limit the rating of the conductor also. If we
Rating
increase
of the
or
conductor wire, yeah, rating of how much current should flow in that conductor, that you can reduce if you increase the number of turns. Yeah.
mm,
But again there will be limited slot area or window area, so you cannot increase number of turns after a certain extent, then you will have to rely on current. So that is again design problem, so that you have to choose it carefully, and how much discretion you go ahead with this, that is all up to you. Okay then, so this is about window area, or this core window area what we discussed. Now the second part is, because we have to complete the area product, for the second parameter of area product is core cross sectional area. So how bigger your core should be, that is the important part. So how bigger it should be? Would you like to answer it?
That depends on the frequency that you can. Everything is dependent, no?
Yes, yes,
In
everything is
AC,
dependent.
depends on
uh,
the energy that we want to store in the inductor.
Energy, okay.
in case of inductor, it is energy stored.
Okay. So the first thing, yeah, frequency is very right, but first thing is Bmax here, right?
Bmax, Bmax,
Yeah,
FNBA.
yeah, FNBA. That is the induced voltage equation, right?
Yes,
4.44
FNBA.
FBN. Yeah. So if you do not know, it is nothing but the voltage induced equation of transformer, or in any terms, if there is certain AC supply. So it is just two or three line derivation. Just go back and see if you haven't been through it. Okay. So area of core will be maximum flux divided by maximum flux density.
Bmax.
Yes. So
Yes, sir.
if you can extend or you can use high-end material whose magnetic flux density saturation limit is higher, you can reduce the core area. Okay. Since the maximum flux, let us assume it is constant, you want certain flux, and you have the limitation on Bmax here. Okay. Now again, the flux will be dependent whether the device is inductor or transformer. Okay. So for inductor, phi max will be L into I max. Okay. Now you have I max, you have L. If you want higher flux, you will provide appropriately current, right? And after this, because anyway, let me draw it. When you we have seen that when voltage was positive, our flux was increasing, and when voltage was negative, our flux was decreasing. So this used to have maximum flux. Okay, so to to provide that much of maximum flux, whether it is flyback or forward, it phi max will be fixed, and that will be dependent on the inductor and I max. Okay, so wherever you can do trade-off between L and I, that you will have to see. And if I will move ahead, then I am coming back to a core. Area of core is Li max divided by B max. It was already there, and the number of turns will be added.
Yes, sir. Here also it is right as now.
Hmm. Here also it will be there. So for I just showed it for one term. If one term will be there, this will be condition. If you have a number of terms, then you will have this kind of expression. And with this area of core we have concluded, and area of window we have concluded. Now we are ready to compute the area product, and let me write the area product for inductor. Area product is A core into A window. A core is nothing but Li max divided by NB max into area window is, it was Ni divided by Kw into J max. Lirms divided by Kw, sorry, N to J max. Okay, so in the same expression we have maximum value of current and RMS value of current, and B max and J max. So if you see, our area product has all the important parameters. Sorry. This N and N will be cancelled, and now it will be L I peak I RMS divided by KW into J max into B max. So area product will be independent of number of turns. Okay. And as you will increase the J max and B max, your area product will keep reducing. So as you use higher and higher values of saturation flux density and current density, area product will keep reducing. Okay. So let us see a problem based on area product. So we have,
So,
go ahead please, if you have any doubt.
sir,
Huh.
the, here we are saying if you choose a higher value of flux density,
Hmm.
then area higher core with a higher value of flux density, the area product comes down.
Hmm.
Sir, there is also another. The size of the core will come down with respect to frequency also, as we have started.
Okay, so you are saying that size of area should reduce by increasing the frequency, right?
Yes, sir.
That is not being reflected in this expression. That what you are saying.
Yes, sir.
Okay. So here, so frequency is indirectly incorporated in inductance value. See, inductance we have seen that was function of frequency. In if you can recall it from buck converter or any kind of converter, if you see the inductance
Mm.
parameter, V is equal to L di by dt. Okay,
Yes, sir. The design equation of inductor will have frequency.
will have frequency. That's what. So inductor is indirectly or inherently having the frequency component. So if you have higher frequency, then you have higher inductance, right? Or sorry, lower inductance.
Lower.
Lower inductance. Is it okay?
Yes,
Yes,
sir.
sir.
Okay. So we will see a design of an inductor of with inductance of 100 microhenry. Okay. And its average current is 5 ampere and peak to peak ripple current is 0.75 ampere. Switching frequency is also given 100 kilohertz, and B max and J max are also given, that is 0.25 Tesla, and J max here is mentioned 6 ampere per mm square. Window fill factor is zero point 0.5. Now we need to compute the area product of this kind of given parameters. Okay, so now we know all the parameters or the expression of area product. Okay, so we can directly go or directly plug in all those formula, all those values in this. But there will be one twist. Uh, this is the inductor current waveform. Let me draw it. So this is IL. in area product, we have this whatever the expression we have derived, that is Li peak into I RMS divided by Kw into Jmax into Bmax. Okay. So based on the Bmax, you can see the data set which materials follow that kind of, or that will be fine if you use this kind of flux density. So that you might refer certain material data set and you see that where it will be suitable, and you please let me know in the next session where this, in which material this kind of maximum flux density will be suitable. And with Jmax, how much area of conductor you should use. Okay. So with the Jmax of, there are two parameters that I am asking. If you could note it, please. So which material for Bmax is equal to 0.25 Tesla. I know all of your answers would be different, but which material would be more suitable, most near to the required, most suitable, and area of conductor, how much area of conductor you will use to cater the J max of 6 ampere per mm square. Okay, so you should think about these two factors or parameters rather, and you please let me know in the next session. So here I will just plug in 100 microhenry, and I peak is nothing but 5 plus 0.75 by 2. So I peak is 5 plus del IL by 2, so 0.75 by 2. So 5.37375 would be appropriate. 0.75 by 2. Yeah, into I RMS. How much will be RMS of this kind of current? Kw is zero point 0.5, Jmax is given 6 ampere per mm square into, because we have to convert ampere per mm square into ampere per meter square, into B max is 0.25 Tesla. So one thing is remaining, IRMS. How to compute IRMS of? Obviously, the standard formula of RMS will always work. Okay. But if you can remember, I have told you earlier that RMS of triangular is,
It's I naught plus del IL by 2, 12.
okay, that is correct. But Y12, Y12, you are saying? You are
So
saying that RMS is I plus I by
no, it is root of average plus del I by 12.
root of average plus del IL by 12. Okay.
We derived in the last class this thing.
Did we?
We derived in one of the previous
Okay,
session.
other session. Okay, okay. Okay. So that is good. So I square plus del I by 12. So I hope everyone is aware with this kind of value of RMS of triangular waveform. If there are certain doubt about it, we can clear it. Otherwise, we will be happy to move
Sir,
ahead.
I think square won't
Sir,
come.
we have to, we can take that DC value, DC IRMS is equal to DC factor plus that AC factor
Yeah,
RMS.
yes, yes,
What is
that,
that? That is I delta I by 2 divided by root 3.
yes, yes, yes. That is the
That is
approach. Yeah,
uh,
yeah. That
easy approach.
that that is the easiest approach. Yes. So
delta I by 2 by root 3.
delta I by 3, and since here we have half of the time period, so
Yes.
that will 2 will go in denominator, and it will be effectively del I by 2
Del I
into
by 2.
2, and 3
Hmm.
was already there, so this will be the whole value.
Sir, please tell how did you get this, sir?
Okay, this one, see,
Del I by 2 to 2 into 3 root of 3.
see, oh, sorry, this del I should be outside. See
Sir,
here,
I think
yeah, yeah, you are saying something?
in the previous equation also the square won't come. I think
A
the squares
square,
won't come. I think.
a square
Yeah.
root, you are saying it will not come?
No, square root will be there, but inside the square root the squares won't come. I think.
No,
Okay,
no. This previous equation, the upper
okay.
equation is same as whatever he has, sir has written this, because
See,
this is RMS quantity of ripple and plus I square, that is DC quantity.
see, RMS of DC will be same. So that's why
Same
I wrote I square. But the
I square, that
RMS
is this.
of this ripple, that will come out to be del I by 12. And
And how
will
it is coming, that he is telling. Okay.
that I am about to tell you.
Yes.
Okay.
Is it
Carry on,
fine?
sir. Yes.
Okay.
Yes, sir.
So,
Yes, sir.
yeah, see. So, for any triangular waveform, if it is like this, we have derived, or if not derived, you can anytime derive. If its amplitude is A, then its RMS is, let us suppose x RMS is A by under root 3. Or you can say A square by 3, that will be x square RMS. Okay.
Yes, sir.
Okay.
So if it is A square by 3, and now here the amplitude is itself, if you reduce it or subtract it by average value, it is del I by 2, right?
Okay.
So now the magnitude is itself del I by 2.
Uh,
So let me plug in here in the magnitude, right? So at the place of A, I will write del I by 2
okay.
square and by 3. So if I will write it, so it will be del I square divided by 4 into 3, that is del I square by 12.
12.
So, and if you write XRMS, that will be del I by under root 12. So that's how I concluded there.
Okay.
Isn't it easy?
Yes.
Yes, sir.
Yes. So, yeah, so let me write IRMS is equal to under root I square plus del I square by 12, and del I we know it is 5, so 25 I square, and del I is nothing but mm, ripple current is 0.75 ampere, so
Okay.
0.75
So
square divided by 12, so it will be approximately,
5 amps.
yeah, it will be approximately 5 ampere. So if ripple is less, then yeah, RMS will be approximately equal to average, even RMS. So now we computed IRMS, we will just plug in there in area product, and we will get the area product.
so by thumb rule, if the ripple is 5% or 10%, we can straight away take as I is the influential quantity.
Yes, yes, that we can conveniently take assumption, yes, because that is not affecting so much. So yeah. Into IRMS. I peak was 5.375, IRMS is 5.5 into 0.25 into 6 into 10 to the power 6. Okay. So it will come out to, if you compute it, you will get some 3587 mm square. Okay, so any doubt about this question? And two parameters that you need to think about: area of conductor and material for this kind of Bmax. Okay, we talked about design of inductor. Now we will see about design of transformer. Okay, so again we will do the same thing about transformer. We will first try to compute core area and then window area. So for core area, window area would be same for both the devices. Core area, there will be minor change. Okay, so here, oh, I think I have lost the connection. Formal, we have completed the design of inductor. Okay, so design window area will be same for both the devices, as I told. It will be same in the case of transformer as in it was in inductor. The thing is, core area expression will be changed slightly, that we will see. So core area was nothing but it was dependent on peak flux divided by maximum flux density. Core area. So there we equated maximum flux is equal to Li by N. So phi was equal to Li by N. Here phi max or phi will be dependent on voltage, right? Generally inductor is mostly dependent on current source. Here flux we will relate it with voltage, because in transformer we will we always excite the transformer with the help of voltage source. So we connect an voltage source in the primary winding and it will excite the core. So here we will try to relate, and as we know, we nothing but 4.44 into F phi n. So here phi max is. So now we will plug in this value. So phi max will be V divided by 4.44 F into N, and Bmax was already there. And since we are exciting the winding from supply sides or primary side, so we will take V1 and N1. And frequency, it will nothing but the switching frequency. And 1 by 4.44 we will take some common here, or we will take it, or we will call it a factor K into V1, or V in rather you can say, supply, divided by N1 into Fs. So now I eliminated Bmax. Why? I should have eliminated it from here only, because phi max is nothing but Bmax into area, right? So if you are having phi max divided by Bmax, it is nothing but indirectly the dimension of area. So, and generally in with converters, this, I think some comment is there. Okay, no. So this K factor is nothing but the duty ratio of the forward or flyback converter, whatever we will use. So K is nothing but the duty ratio. So if you have certain kind of duty ratio provided, it will be D into V in divided by N1 into Fs. So that's how transformer in forward converter you can go for. So this why the peak flux, right? So now if you just plug in core area core expression, you will get this K into V in into N into Fs into Bmax. Because this peak flux will be Bmax into area, so I just brought back the Bmax here. And anyway, Bmax is an important parameter to decide the material. So now if I do the area product AP, so I will have to bring back that core window area from the first equation or from the inductor's derivation which we have done already. So if we do so, so we have this K factor and V in into I RMS into KW window area factor into Fs is here from here and Jmax from window area factor and Bmax is from this area. So this is the window area factor for transformer. More or less same, just that one current we have removed. And can you guess which current we have removed? We have removed the peak current parameter with input voltage, right? So peak current parameter was present in the design equation of inductor. Here we have input current and sorry, input voltage because it will be excited with voltage. And more or less all the things are same. And here you can see frequency component is coming explicitly. So since inductance parameter is absent from this expression, you can see that frequency component is coming explicitly. Otherwise, inductance is an indirect representation of frequency, but we have removed it from here, so you can see it, frequency is coming in this expression. Right, so based on this expression, I am posing a problem of design of transformer with forward converter and you just try to solve it on your own. It is not a tough problem, it is very easy problem just based on expression. So you just need to design a transformer in forward converter whose parameters I am providing 100 kilohertz of switching frequency. V1, V2, V3 is all are equal 30 volt. RMS current in each winding, all those three windings is 2.5 ampere. Okay, you can choose Bmax as same in the upper problem 0.25 Tesla and Jmax you can select as at slightly reduced 5 ampere per mm square. Now Kw and D is given. Kw is zero point 0.5 and D duty ratio of forward converter is zero point 0.5 is given. Now you just need to compute area product. Okay. So
Sir,
yeah,
sir, in the above expression of area product, we have derived there is a term called K, this on the numerator.
What I have written, could you please repeat that?
No, no. On the numerator, there is a factor k.
Huh.
Sir, from how did this came?
This
This k.
K came from that 1 by 4.44 we eliminated with K factor, right?
Okay. This 4.44 is k. Okay. 1 by 4.44 is k.
Or might be some other constant what we have eliminated. V in is there still, right? So phi max is V in divided by 4. V in is still there, Fs is still there, N1 is still there. So, okay, no. B max. B max into 4.44 will be K. 1 by B max into 4.44 will be K. Is it
Okay.
right?
Yes, sir.
Okay. See if there are certain errors in this expression, please let me know if it is there. I will see, but I don't think it should be an error because 1.44 is straight away an integer, so it should be multiplication of 1.4, sorry, 4.44 into B max because B max anyway we are reducing.
Then an area product, sir, if it
Sorry.
is k is equal to in area product
Huh,
in
huh.
AP,
Mm-hmm.
that k into Vn IRMS divided by KW FS Jmax Bmax will not be there if it is already taken. K
Okay.
is equal to 1 upon 4.44 into Bmax.
Okay. Yes,
So,
yes, that is also true. Yeah. And just
that will not.
okay, so let us verify it right here. 4.44 into F phi max into N into B max. Okay,
Yes.
this B max is here. Now we are saying that phi is peak value of phi is nothing but mm, okay, peak value of phi is nothing but V in divided by peak value of phi is mm, V in divided by N1 into Fs into K. So this is the expression of peak flux and it should be V in divided by 4.44 F into mm, N. Yeah, so K apparently it is coming out to be 1 by 4.44 because F has B max and A factor inherently, so It is 1 by 4.44, but it will be very less compared to zero point 0.5. So how in literatures it is mentioned that it is equal to duty ratio? So that we will have to see. Okay, so you refer the book Ned Mohan that I told, and I will also see how they are saying it as duty ratio D, which should not be equal to 1.44. So, however, they concluded with this expression as k equal to 1.4, 1 divided by 1.44, and they led to this factor. Okay, so if you remove this k from here, then you will have the area product of 4.44. Okay, so you consider now this expression, and the duty ratio will again have to be taken care. That will come handy with input voltage if you know the output voltage and so or the number of turns if you don't know. However, area product is independent of number of turns, but for anyway, if you required there, then you can use. Is it okay now?
Yes, sir.
Okay then. So
Sir, we have not discussed the flyback transformer, DCM and CCM.
that I think I have discussed it on that day.
Is it?
Have you seen the recording of that? Because
No, no, no. Is it over?
yeah, because I think you were not there.
I wasn't there. Yes,
Uh-huh.
sir.
So I think I have
On which
discussed it.
day?
On the next week, what you told me that in next session we will start from there.
I mean, last Monday or something.
Last or last to last, I guess. Because
Last.
last session I started magnetics, so I think before that week I must have discussed that.
Okay, okay. I will see that.
Okay. Anyway, if it will be not there or if it will be pending, then we can discuss it again. So,
First, I will see that in the.
yeah, sure. Okay then, so I think it's time to wind up the
Sir,
session.
Thank you, sir.
Thank you very much.
sir,
Yeah,
sir, next class, will you please tell about the tools to visualize the skin effect and approximate?
okay, definitely. I will look that and I will see if it is available online.
Okay.